But when you're using gases, I will give an example of this because this happens when we are talking about a very important process like ammonia synthesis, right? You have nitrogen and hydrogen. So ammonia basically feeds the world. And if you want to increase ammonia production, you need to increase the pressure and all. So in that case, you need to use this kind of the pressure version of this equation. So these two are the expressions. Just keep a track of this, and I will show it to you, and we'll deal with the practical example. So yeah, some basic, understanding of these things. Like for example, when you have the forward reaction and the reverse reaction, you can always form the inverse. The equilibrium constant is basically the inverse of the forward process or the reverse process. So I think you guys must be already knowing this, but I'm just rehashing it quickly. And when you're considering solid products and gas, your equilibrium does not depend on the solid product or the solid reactant. Or even if it's a liquid, it doesn't feature into the equilibrium expression at all. So all these things we use when we're doing a chemical process, like we are calculating certain aspects of the chemical process. We use these particular framework of rules. Okay. So now some of the processes are like this, like for example, this reaction, right? I mean, the equilibrium constant is very high, but it never happens in the normal conditions. Because, if you want to do this process, mostly it's done either electrocatalytically or using very high temperatures. You can do this, like water, especially the water splitting. It's a very big deal now because hydrogen economy and everything, right? So you want to make green hydrogen. For water splitting, you need to use electrolysis or something like that. Okay? So here what happens is that if your the value for a process like this, the K is very high. Okay? The K is 3 into 10 to the power 81. It always favors the forward equilibrium. Like if you add this H2, it's going to push more forward towards the product formation of the H2O, right? In this particular case, it's okay. Now, this is a very important reaction because this is the water gas shift reaction. This is how most of the hydrogen that you're currently using for most of your processes is done through this. And this particular reaction, I'll discuss more in detail later. What happens is that it's kinetically limited at lower temperatures. At 250 degrees Celsius, the equilibrium is not, you get very little reactivity. It's very slow. It doesn't happen as much as you want it to. So you have to operate it at higher temperatures, above 250. And at that time, the K will change. When you change the temperature, the equilibrium constant will change. How much of it is going to react and how much of it is going to form hydrogen and CO2. Really, we don't care about this, but we care about this, right? And then you have something like this. This almost never happens because the forward reaction almost never happens because you're going to have CO2 and it's going to stay as CO2. It's not going to form the carbon monoxide and oxygen. So this K, right, is always determined experimentally. You need to do a reaction, you need to measure the concentrations of those things and then use the expression as we have it here. And you can determine it. So that K is always fixed for a particular temperature, the equilibrium constant, right? So it helps many people like in process design and especially in reaction chemistry and catalysis. We use this in kinetics to understand how to optimize the process.
How do they measure this small value of K?
So this, I think, they may be using large concentrations of the gases, or they may even be feeding this carbon monoxide and oxygen, and they look at the rate of the reaction and like how much of the product is formed at any point. Like for example, if you use gas chromatography, right, you can find out, like you can use some standard color calibration and find out how much of this product is forming at any given time, and then you use this expression, right? So, but then if the concentration is very low, like you have to make sure that you put large volumes of CO2 to get even a small infinitesimal amount of CO or O2. So, and then you get some approximate calibrated concentration of these products. Then you plug it into the expression and you can get that value. But yeah, so the thing is, when they get this value, they usually do it through this experimental, they have to use some kind of chromatographic technique or some kind of tool to identify this concentration, even if it's very small. That technique has to be very sensitive. So then you get this. Because this reaction almost never happens. This conversion of, unless you use very high temperatures, you will not. This is probably for a particular, I don't know what temperature this is, but they must have used a lower temperature than normal for this to disproportionate into CO and O2. Yeah, but this is not even a useful, it's not a very useful reaction.
Raghu,
yeah.
If you look at that reaction, 10 minus
92.
I think statistical mechanics will help you to calculate these things.
Yes.
So I think when numbers are that small, yeah, just essentially even a number that comes from calculation.
Yes.
I think to really measure 10 power minus 92 as your K,
Yeah.
and to write the equilibrium reaction, you have to measure O2 to drop to concentration something like 10 power minus 15 moles or something. And then if you say carbon monoxide is 10 power minus 15 moles,
Yeah.
there's a square of that. And therefore it becomes 10 power minus 30 and 10 power 15, that's 10 power 45. You're still not going to get to minus 90.
Correct. Okay. Maybe.
Right? That's a number that you probably estimate from statistical mechanics, which can help you calculate these things. And as you said, you rightly said, 10 power minus 92, who cares?
It's not going to happen at all.
It's not going to happen, therefore you will today have to try doing this reaction.
So, but mostly the thing is because for us, when we use these processes, for example, so I worked on CO2 hydrogenation and then DRM, right? So the temperature matters. If I do it at a lower temperature, I cannot get what I want.
That's another thing that people might say to get. As you said, you don't know what the temperature.
Yeah, they must have used a very low temperature for this,
Yeah.
not a
There is some other temperature, it is more meaningful that I can measure it.
Yeah.
And then I do the K at various temperatures.
Yes.
And then you have
It's going to be different.
I think the Kirchhoff equation which extrapolate and get at room temperature. Which of course might be 10 power minus 92.
Yeah, because maybe I shouldn't have put this example.
I think that's the.
But the thing is, like,
No, it's a good example just to say that, this reaction does doesn't happen. There's no need to consider as a viable process in an industry.
Yeah. So it's just to show that, when you depend on the looking at the value of the K, we can decide where is the equilibrium shifting. So yeah, so basically this about the equilibrium, right? So people have been familiar with it. So we use this as the trick to trick a reaction to go forward in the way we want or go back in the way we want, right? So you can change the equilibrium by various factors, okay? So the main thing is the temperature is what that changes your equilibrium constant. But if you change the other aspects like the partial pressure or if you change the concentration of the gas, the equilibrium is just going to adjust. It's going to look like, for example, if you see this process. So here, right? If you add more H2, it's going to shift backwards. Okay. And those kind of things. So if you add more H2, it's going to shift forward until the equilibrium is established. So even if you start with this, if you start with the products for this reaction and you allow it to, simmer for some time, it's going to establish this equilibrium. Right? It's going to form these other products, the reactants. Okay. So these are some things like, so basically if you want to go for the equilibrium to go your way, you need to add something to shift it in that particular direction. For example, what we do with, for example, I told CO2 hydrogenation. You know that your conversion is going to stop at 35% of the product. Like you want CO2 to convert to methanol. So what you do, you add some more amount of hydrogen. If you increase the amount of hydrogen, you get more methanol. Or if you add some more CO2, it's not going to ultimately change the fact that your conversion is limited at say 35% CO2. But you can get more methanol if you want. Right? So this is a very important process. So I'm going to use this as the example of how you can trick the reaction into forming what you want, right? So again, here the K is, the equilibrium is always towards the reactants. It's more towards nitrogen and hydrogen. But if you increase the pressure, for example, or if you increase the temperature for this reaction, you can get significant amounts of ammonia. But nowadays, what we do is we try to develop catalysts or change certain the way of heating. For example, we use conventional heating, that is just using a furnace. But then sometimes you can use photothermal, like using two sources of energy and reduce the pressure. And then you can force the equilibrium to go towards the product. If you add more of this hydrogen, it will shift towards the ammonia synthesis again. So yeah, so this is what they do. So you start with the initially when you have hydrogen and nitrogen under the right temperature and under the right pressure, it's going to form ammonia. It's going to keep forming ammonia until it establishes the equilibrium. Once the equilibrium is established, it's not going to go further anymore. It's just going to be like, stay. Both the formation of your products and reactants is just going to heteroconvertibly keep changing. So then you add some hydrogen, again, it increases the conversion. So it's always like this. So this interplay between the Q, it's a reaction coefficient. Like this Q is the expression is the same as your K, but you change something. When you add something, you can push the Q to go towards the K.
What is the difference between Q and K?
So Q is just this thing. So like if you have the same expression, right? You have this, but its equilibrium is not being established yet. You have
The concentration at any point of the
at any point, even before the equilibrium is established. So if you have the values of what can happen is, if it has been experimentally determined that the K for a reaction is this at this temperature and this pressure, and you have a random bunch of concentrations of the reactants, and you calculate K, and the K is less than that value, that means Q has not been established yet. So if it's like, so it's just this, and for any given concentration, if you are having a certain concentration of the product, if it gives you the value, when you plug it into this equation, and you get the value that is equal to the equilibrium constant, then you know equilibrium is already there. But if you have those concentrations and it's less than the value of K, right? Then it's Q. It's not yet approached equilibrium. It's on the way. It's going there towards establishing equilibrium. So Q is just to understand, it's not very important parameter. It's just to for academically for calculating, and you want to know how far your reaction can go. So this is calculating.
If you have one value, that means in which direction I will be.
Yeah, exactly. So which side the equilibrium is going. So if it's still less than the K, then you know that it's shifting towards the right of the equilibrium. If it's more than the K, shifting is going to eventually come back to the established equilibrium at that particular temperature and particular. So yeah, so the main thing is it's a temperature. Like when you play with the temperature, it's when you make sure that you can get what you want. Like for example, reactions like now, most of in the globe they're trying to do carbon management, right? So CO2. So when I was doing in breed, I was working with CO2 hydrogenation. So when I went to KAUST, the Aramco project that we were funded on was dry reforming. So there, we're using 800 degrees Celsius in the reactor, but the CO2 is completely converted to syngas. So in that case, if I use like 750 or 700 degrees Celsius, my CO2 is not going to be converted as much as I want. But I can get almost 100% conversion because the equilibrium for that is around 98 to 99% conversion of CO2 at 800 degrees Celsius. So the temperature plays a big role in this. So and when you have that particular reaction, the dry deforming of methane, and you form the syngas. The syngas is more reactive. The carbon monoxide is more reactive to form your liquid products. So there I'm indirectly converting almost 100% of my CO2 into ethanol or methanol. So we can play around with these factors and increase the particular process. So yeah, basically the K equilibrium is less than this particular. Basically if this is the value if you're getting from your particular concentrations, then you know that you're not yet establishing the equilibrium.
So for this Krea process, right?
Yeah.
If we increase the temperature, which way do you go?
So in this particular case, so I don't have. Okay, the enthalpy is here, right? So I don't know about the delta G of this reaction. This is an endothermic process. Yes. So if you increase the temperature, it's going to increase more. Is it an exothermic process? Sorry. So then if you increase the temperature, it's going to go back to it. That's not good.
In fact, I think at room temperature, the K for the number like now process is something like 10 power minus 10 power minus. Yeah. Then the data is so low you can't use that.
Yeah. So for this we use usually in my research talk I'll talk about the pressure. Like when you use different catalysts, you can reduce the pressure. So we generally this reaction right now we are conducting only at 400 degrees Celsius, not increasing the temperature too much. 400 degrees Celsius, then we clear the pressure and then catalyst design. Okay. So mainly the problem in this reaction, right, is this. Activating the nitrogen. So if you cannot activate this, the reaction doesn't happen. And then the other problem is so most of the best catalyst known till date is ruthenium. But ruthenium, you cannot go to very high pressures because this will poison. So temperature, they don't touch the temperature too much. They try to do 300 to 400 degrees and then play with pressure and catalyst. Yeah, so then okay, this part is going to be calculations. I'm just going to basically what I've compressed in these slides is what I went over to like 1 week to for students. But the next few slides is just going to be some calculations about how we use this particular the ice table. Okay, So in this, you can determine an equilibrium. If you have an algebraically, you can determine it, or if you know the concentration of one of the products, you can determine it by establishing the equilibrium. Okay. So this is the ice, basically an ice table. It's the initial change in the equilibrium. Like if you know the initial concentrations of your reactants, right, and you know the equilibrium concentration of your product, so you can determine the rest of the aspects. So you can just remember that here you have 1 mole of hydrogen giving you 2 moles of hydrogen right? And the same with this. So you have to account for that in the change, right? So this, because like I told you, like 1 mole of this gives you 2 moles of this, you can plug in the values of the change, whatever it is. And you have because this is increased by this, and you know the equilibrium has been established. They tell you everything, right? They haven't given the constant. They want you to find out the equilibrium constant. So then you get the equilibrium, all the values of the equilibrium at that particular value using this alone. You had this and you had this, and you found the other values using this ice table. And you plug it in, and you can easily get the constant, the equilibrium constant. And this particular value is only for 448 degrees Celsius. Okay, if you change the temperature, you're obviously going to get different concentrations, and the equilibrium constant is going to change. So this is when you are doing algebraically. Okay, you have the initial concentrations, but you don't know how much is the concentration of your all the species that, or you don't know the Kc. You know the Kc value also, but then you're trying to use a ice table. So first you always write the expression, and you make the ice table. So you have the initial concentrations of the products, and you put it in terms of, again, the molar ratio, like 1 mole of the 2 moles of this is going to this proportion into 1 mole of this and that. And you have the initial concentrations of the, so like I said, right, you can establish the equilibrium from either side, from the reactant side or the product side. And the same, the Kc expression is very straightforward. You have basically all the coefficients of the reactants and the products. You put it in, you get the expression, and then when you solve for it quadratically, see, in this case, this is a very ideal scenario. Okay, like you're going to get this very perfectly squared version, where once you solve it, you're going to get only one value from the x, right? So there's no confusion here. The reason I put this particular caveat is that once you have a reaction where you have different values for x, you need to take your judgment. For example, when you have partial pressure, right? If you get one value of x which is negative, you need to realize that that's not true. It cannot be happening, right? You cannot accept that value. So in that case, you have to decide, you make your judgment about which value of x to take. Here it was pretty straightforward. You just get one value for the x, and this is absolutely what it is. It's the only value. So yeah, so this is the strategies to, like, if you have these concentrations and if you have a process, you can find the equilibrium using this ice table, like the initial, the change in equilibrium concentration, right? So now basically these two examples just to show you, like, if you have the known concentrations and if you have, if you don't know the concentration, or if you don't know the equilibrium concentration, you can always determine it pretty simply, experimentally, if you have the values, and if you have the method of measuring what a particular amount of the concentration. So yeah, like I was saying, right? So the water gas shift reaction. So here, this reaction is very important because most of your hydrogen right now used in fuel cells and many of the applications is done through this process. Now they do steam reforming also, where they do, again, that's a high temperature process. It's around 900 degrees Celsius. They combine methane with water and they try to get hydrogen and CO, gas. That's another process, but this happens at a lower temperature. It's around 600 degrees. They don't go too high. So again, equilibrium is operating here at different temperatures. You need to know which temperature to use, and catalysis helps here. Like if you get a good catalyst, you can get an optimum temperature, good conversion of the products of your reactants to get the optimum amount of hydrogen that you want. So equilibrium plays a role. Understanding, measuring this experimentally and finding out what equilibrium at for what catalyst, what temperature helps for optimizing this process for more hydrogen production. So this is the process that I mostly dealt with, and in my time at KAUST, and we were making this nickel molybdenum based MgO catalyst, and we were mostly dealing with this process because it was the most convenient way to completely convert CO2 into hydrogen and syngas. I mean, like hydrogen and carbon monoxide, right? This is my last slide, by the way, so I'll just spend a little more time on this, why it's important, right? So here you have two endothermic processes, moderately endothermic processes, and two exothermic processes. So when you increase the temperature, these exothermic processes are not favored that much. When you go higher and higher to the higher temperature, right, you avoid these two processes which you don't want. And these two processes don't happen to that extent. If you have the right catalyst, you mostly get only this reaction as the major operating reaction, right? So this particular product, this syngas, carbon monoxide and hydrogen, is very useful across industries because that's what they use to make most of the. It's called syngas for a reason, right? I mean, even nitrogen and hydrogen is considered syngas, but that's only for ammonia. Here, syngas, you can make all your kinds of polymers. You can make your methanol, ethanol, higher alcohols. There's like a whole library of products that you make using syngas, carbon monoxide. So this is more, and carbon monoxide is more reactive than CO2. But understanding chemical equilibrium and the thermodynamics of the process and at what temperature it works best will get you the optimum reaction conditions for any catalyst that you try to develop. Right. So yeah, so understanding why equilibrium is important can help us improve the many of the big industrial scale processes that we deal with. Yeah, so that's my talk for this. I think I conveyed some idea of what chemical equilibrium is. And if you have any questions.
I think I have a question about this slide.
No, this one? So this is like the beacon. It's like it's a huge monument in the on the coast. Like I think I don't know if I have a proper picture of this place.
But this is not
this is simulation. This is simulation. This is just like a AI. I mean, whatever the.
Oh, okay.
I'll show I can show you the actual.
Okay. No, I thought this is like a fancy carbon capture tower.
No, it doesn't do anything. It doesn't do anything. It just stays there. It's for beautification processes. No, but it's like so. Oh, there's no internet here. It's fine. So because the Kaust community is like so we call it a golden cage, right? So we're there and we need something to look at. Like so they make all these fancy stuff, like a very good restaurant within the campus. Right? So people can visit, like family. A lot of families are there, so they go here and it's like a walkway. Especially now and during November, December, it's very nice to meet.
But since I'm not a chemist, I think I will go on that. I'll be really like a student. So, in your definition, very first page on this definition of K.
Yeah.
Is there any simpler way to understand? Next page. Next page, where you have written them. Why this C power C, the exponent is actually the numbers that are coming in the equation, the number of moles.
I mean, like it's just the. I mean, this is the expression that we just use to determine the.
Must be a reason of why they have different expressions.
I think what's happened is my feeling is this. All of this, right, was ultimately determined experimentally. Like they.
Absolutely.
So
K
yeah.
is determined experimentally, but a K can be computed this way.
Yeah.
That must be reason why.
No, that's what I'm saying. So when they did this, when they knew a reaction, like they balanced an equation and they did a process and they balanced the equation and they found that these concentrations and the exponents of those concentrations affect the experimental determination of this. Then I believe that's how they would have arrived at this expression, because this doesn't look. I mean, like Sir said, statistical. I'm not very familiar with statistical mechanics, but I'm guessing that most of the stuff that was done earlier, the initial determination of what expression works for a process, was done to some trial and error.
Fine, but now we may have some understanding.
Yeah. So this is one of the conflicts I have with like what do you call this, theoretical determinations. Sometimes, most of the time, they get it right, but sometimes it's off from what is experimentally found. So like if I do a experiment 10, 15 times and I get the same result, it's cumbersome, of course. I have to keep on doing it to get, the final expression, to get the final data. But it's reliable to me because I'm seeing it. I'm seeing it happen and I'm getting the values that are not changing very much. So there's some pattern here. Whereas when you do theoretically, if you try to predict something, you're going into very risky territory. Like you don't have all the numbers, you have half a picture, but you're trying to build the full picture. It takes some time for that, both of these things to match very well, both theory and experimental. So my understanding of this particular expression, like it's basically taught everywhere in undergrad right now. It was done after many, many years of trial and error and seeing that, this method of just using the exponents and the concentrations of your products it seems to give you a number which makes sense. So they've coded it and established it as formula.
If you go to step one, go one step back and see where how K is actually defined.
Yeah.
It is defined as the ratio of the rate constant of the forward and the backward.
Yeah.
The rate of the forward reaction is going to be K into A power A into B power B. The rate of the reverse reaction is rate C, constant of C power C and B power D.
Yeah.
And these two rates must be equal at equality.
Yes.
Now, if you put all that, you will get that. So K basically, let's say C, that is the ratio of the rate constants.
Correct.
Yeah. So it will be true only the order is same.
Yeah. We are assuming that the stoichiometry gives me the order. Now, if you have a situation where the stoichiometry does not give you the order, you will get into problem here.
Yeah, actually, so this expression is derived from the like.
Right, this expression
Yeah.
of cases of thermodynamics.
Yeah.
So, but even
Usually
the
comes-
kinetics, if you get the, if you get
Then
the,
the reaction is very strange. In the sense that the stoichiometry won't give you the
Yeah,
order, then you will have a problem in writing.
Yeah.
But in most cases, the stoichiometry should be the order. Therefore, it's order.
I mean, I'm not sure if I answered your question, but I'm basically saying that these expressions that we take for granted and we say, assume that, this is it.
No, I agree. I was only thinking now that I agree. Initially, probably, people by trial and error, they figured out this point actually captures what's really going on. And because I also see, to me at least, it appears, if I write down the differential equation for this forward reaction and backward reaction, I can actually interpret it as a ratio of probability for the forward reaction.
Yeah.
Rather, probability for the reverse reaction because it is probability for the reverse. Once it is probability, the exponents are very natural. So why that should be a factor C? Because it is a probability that it will collide with itself.
Okay.
No, actually, it is the probability. This thing. In fact, you can actually do one thing. That's how I handle it. I take A, I just do a reaction where A goes to B. So it's simple. I start with, let us say, 1024 moles of A. And then I assume that at a given, let's say after 1 minute, 50% of A has gone to B. That's again a probability. 0.5 is a probability. After 1 minute, A has gone to B. So 124, 1024 at the end of 1 minute, 55 plus 5. Now I'm going to assume that the probability of B going to A, let us say, is also 0.5. So at the end of 2 minutes, half of this will become that and half of that will become that. And if you run through a few iterations, then you will find that the constants will keep repeating themselves.
Yeah.
So it's surely a probability. Now it is plays the game. You can say the probability of the forward reaction is 0.5, whereas the reverse reaction is 0.2. You will need a few more steps before you get to equilibrium. But then you can just do it on Excel. I asked people to do it on Excel. And it just works on that. So it's essentially a probability. It is a probability of the forward and the backward reaction. But then coming to think of it, rates are probability.
Yeah.
Glorified probability.
The other one, you also said the Dirac principle.
Yeah.
Is it still a principle or it is better?
I mean, see, the thing is, the controversy of the Lee-Chatelet, some people, like there was a professor I had in, it's just an announcement, like basically looking at phenomena, some guy made this Lee-Chatelet made a statement. But my professor, when I was in Iowa State, there's a professor of solid state chemistry, his name is Dr. Gordon Miller. He doesn't like this Lee-Chatelet principle because it's very random, right? You need to have thermodynamic evidence, you need to have actual experimental other evidence to say what is going on. Like, why is this shifting that way or this? But again, it's like what chemists mostly do is we do a lot of trial and error, and then we come up with some grand conclusions based on repeatability. And then say, okay, then we use this as a metric to try to do this. But we need to more experimentally verify things. But Lee-Chatelet principle is not experimentally, it's just seen whatever data was seen from experiments, he made this statement, saying that this is what I'm seeing is happening. I increase this and this increases. If I increase the nitrogen, again it shifts towards the right. So this is what is happening. If I put stress on a particular process, it's going to go forward. So it's like very Professor Gordon Miller.
I don't think because in all sciences, I think disturb the equilibrium.
Yeah.
That is being established. The system will want to get back to equilibrium.
Correct.
And the only way it can get back to equilibrium is to undo what you just did.
Yeah.
That's exactly what you
Yes,
started.
but the thing, like if you see the question he's asking, he's saying that is a very, it's it's you're just saying something because you see it, you observe the data, but you don't have any experimental.
Yeah, it can substantiate what Professor Bush said. Let's say equilibrium quality, I believe it's a thermodynamic equilibrium.
Yeah.
It's a minimum of a free energy or a maximum of a suitably defined input. Now for small deviations, because it's a minimum, it's like a harmonic oscillator.
Yeah.
It will pull it back.
Yes.
So that's precisely what Richard Bronson should be all the time.
Correct, but I'm not saying that my professor in Iowa State, it's not that he disagrees. He doesn't like the way it's used, like the way it's pronounced as, oh no, you know what,
Yeah, I know.
you need to believe him.
What you are saying is the following, that they probably have not, which to me is very fundamental.
Yeah.
You know, all our sciences, whether it's biology or chemistry, anyway, you touch an equilibrium. It wants to get back to the equilibrium. So the only way it can get back is to undo what you did.
Yes.
That's why it can get back. So Nishatya-Brown principle stated that if you disturb an equilibrium, if you try to undo what you did to disturb it, it is exactly the same as doing. But I think people have trivialized it to an extent which is where the problem comes.
So I think that's why he saw it.
Teaching Nishatya, I think it has been trivialized.
Yeah.
And therefore,
But even when he said this, right, he didn't have many of the tools to, like, say that exactly what.
no, I would have thought that Nishatya, of course, was well aware of the fact that disturbing an equilibrium.
Yeah.
Restored only by.
I don't think Professor Gordon Miller disagrees with that part of it. It's just that when you say these things, you need to give like data, like the fact that okay, these numbers are involved in this change.
It is qualitative. That's what Nishatya principle is qualitative. It does not give me a quantitative.
Yeah.
That Brown principle talks about the direction of a process.
Yeah.
So
That's all. It's like a law.
Yeah, but exactly, it's a
Yeah.
law. I'm saying, see, literature then maybe it was a principle.
Yeah.
Now that our the kind of class that we have on thermodynamics, it's not a principle anymore. It's a derivable.
Yeah. But like, I mean, it's like, so when we use it, we still refer to it as a principle. I don't know
It's
why.
okay, it's for like conservation of energy principle, but actually we can show conservation of energy is a consequence of my total forces being given at time.
Because the first thing, the example you gave was, carbon dioxide equation, which converting to methanol. So then your problem is, eventually it will lead to equilibrium. It is far away from getting the conversion stations. So then again, coming back to the fact that the methanol is solid in the water and carbon dioxide and you are hydrogen is not. So if this reaction was done in such a way that it was always circulated through water,
Yeah.
you would keep pulling the methanol into water,
Yeah.
upsetting the equilibrium, and therefore more of it should form methanol.
So they try to do that, but like again, it's still eventually the equilibrium. It's very small. Like you keep on doing it, right? It's very cumbersome, and when you go into a larger scale reactor, it becomes problematic. So most of the times, what we do is we try to develop catalysts, but to increase the selectivity to the methanol. So you get these side reactions also. You get formation of carbon monoxide and water also. The undesirable product. So selectivity has to be improved, and then you need to make sure that all the CO2 gets converted to the methanol. It's difficult. That's why we said that the better process is through DRM. Like DRM, get all of it converted to syngas first. Like carbon monoxide and it carbon monoxide is more reactive. You can find. Yes, mutations have already studied all this, right? 11 and 12. Very basic stuff. I chose it because I already thought this in I'm saying.
Raghu, just I wanted to ask anything that would you be interested? So this is physical chemistry topic you chose basically. So what is your primary interest? Like would you be interested in teaching organic, inorganic, physical chemistry?
So I thought when I was there in Iowa State, I thought organic lab. So I can teach organic chemistry. Then analytical chemistry, inorganic is also fine. I haven't done any inorganic chemistry, but since I've been working on inorganic chemistry, but mostly because I chose this because most of my time that I was in Iowa State, I was teaching general chemistry, right? So most of the general chemistry I was teaching it for like first year students, like who were medicine majors or biology or chemistry. So I was familiar with it, and maybe I'm not as familiar as I was chemistry student, but it's more comfortable teaching.
So this is not a question about what you spoke about today, but now with so many different concepts of experience, we will think that some concept that we learn together, like the UG, you feel that maybe that's not the right way to teach that concept.
The thing is, mostly in my UG and all, right? People went through the motions. They would just teach me something because they said, okay, this is part of your syllabus. At that time, I didn't give it much thought, or I didn't care about it much. But now, when I was doing my research and teaching students, I realized the relevance of this. So, when I was doing my PhD, all these aspects, the kinetics, this is not just me, even my PhD boss was understanding that. Whatever, some of the slides that I'm showing you here are his templates. So, when he was teaching it, he realized that this is because we are a catalysis lab, we have to use kinetics a lot. So kinetics is mostly, if you see in the undergrad and all, we just teach it as formula. Okay, you do this, you will get the forward reaction, get this, and get the rate of the reaction, determine the order of the reaction. That's it. No example, real life example is given. Why is this relevant? Because most of the people who are going to take chemistry now, they're going to ask us, okay, how are you equipping us for the real world? Now India is pushing on this hydrogen economy, on this catalysis. So we need to give like real examples of these. And I'm hoping that if I'm going to be teaching, I incorporate that. In my when we were taught, we never realized. So, and even the differential equations are all slow. Slowly, I'm realizing all those things will come into picture. How we use this. I don't know if I'm answering your question.
No, I was referring, I don't know, maybe I'm not understanding what you exactly said. This is one I agree. At least you would like to do examples so that sort of motivates or puts the topic in a context. So students appreciate. I'm asking slightly different question. Let us say you want to teach kinetics. They taught you in a particular way. You said they investigated formulation.
Yeah.
Now, if you want to introduce, how else you will introduce?
I will use it with these real life examples, like these real life processes.
How will that help them to grasp the kinetics?
Because
They understand the relevance.
yeah.
But
So I will
help them with that.
it'll so what is going to happen is most students who come to a class, they're going to think about, okay, I need to learn this to get the grade. But I'm going to tell them, like, okay, you learn this now, don't forget it later, because if you go into this line of work, this is going to be relevant then too. It's not just relevant now for your marks. So I'll put some real life examples.
So that it's a context.
Yes.
I'm saying, how does it clarify the concept? That's what I mean.
Yeah.
Do you have an example of, okay, this is the way they introduced to me, but that doesn't really clarify the idea behind this concept.
Yeah.
But this is the way I will teach so that the concept becomes clear to students.
So for me, to do that is to just do problems. So what, like, for example, this, I made a mistake here was, I just put it like in slides and I put all the solutions. I'm not going to do that way. So the way I did it in the US was, I would put the slides, I would give a gap in between the class, and tell them, okay, listen, try to solve this. And there will be points for this if you solve it. So because when the student does it in the class, he can clarify it then and there. So he needs to be as familiar with the concept as possible. So when he leaves the classroom, there's no doubt about how I should do this particular calculation. Like, he should not stumble when it comes to studying for the exam. Like, in the class, you should have already prepared for the exam. So that, I feel like that the best way that can be approached is only by doing problems in the class. I cannot just keep putting slides of text and images and examples. I need to show them that you can do it yourself in class and clarify it then. So that's how I feel it's going to be.
So maybe one follow-up question. So I will come to the follow-up question. I like the ice level quite well. Is it like in textbooks? It's found
It's on that particular
yeah, I was first time I think.
That's the thing, right? Most of what we learn in the 11 and 12, when I went there, even though they're learning the first year of the undergrad, they formalize everything. They put up like a kind of template to do this in a methodical way, right?
No, I like it too. Yeah, so I didn't see what
This is not common.
it is not in Indian textbooks.
We get it in accelerations.
Really? Okay, so maybe somewhere it got lost in.
For me, when I was teaching, this is the first time for me. When I saw this, the method of doing this was first time for me.
We use something called roll with the chant.
Okay.
That because Buffalo was a chemistry NPR person, so we have all these techniques. It is properly done. So how to solve problems?
The way we solve the problem.
We did call it as.
I didn't call that is our career with we didn't call it I didn't call it.
But it's a nice mnemonic. No,
Yeah, so
it is
this
not something.
it kind of stays with the student, right? So like,
So I had a follow-up question, and that is something that we were debating. So initially, when the chemistry syllabus was built, so for example, in our chemistry,
we kind of thought that, I think in your college also, that possibly the periodic table comes first, and that quantum mechanics interpretation of computers, that is kind of comes in later on, right? So I don't know how our students like it, but we kind of visit that today probably we should turn it around. So we should teach some amount of the orbital and concepts of quantum mechanics, even if it's a graphical level first. The inorganic chemistry, or we call it chemistry atmospheric level, comes after that. Okay, I mean, of course, there are pros and cons. So I think, I don't know if Shiva is kind of asking something like that, or maybe, so suppose in this particular case, what will your be pros and cons analysis? That teaching the classical way, that inorganic chemistry periodic table, and then the quantum mechanics, or the other way. So how would you? Yeah. So freely, like, what is your opinion?
See, for me, the thing is, what I realized is like the periodic, like that's the thing I would do for periodic table, especially bonding table is we do that. But the periodic trend, like understanding the periodic table, because that is going to be the thing, right? It's going to be the Bible to whatever chemistry they do, but especially for inorganic chemists, they're going to use the periodic table about the trends, understanding how these metals behave and all this. But I would go the classical way. Okay. Starting on errors, they need to this can go to the templates that we've been using forever. They go into this for longer. So I will just go there. Because if we bombard them with quantum mechanics and like all the other stuff in the initial phase, they may not. They might be a little lost. Yeah. So it's there.
Part of the topic so I don't think it's not supposed to. I don't know because they teach you not. Okay. So they show you all the molecules that way of it. And the next page, they will tell you there are exceptions to the object group. There will be another 14 examples where the molecule is not away the object group and still stable one. The student is really going to ask the question, if there was such a only exception, then why was the rule in the first place? But that's it, it developed. Time, that's the way it developed. Very quickly they realized that object group was really not a big deal. Probably molecules. So I think when we teach it now, you know, the object tool and then the exceptions and all that. Let's say the object tool was what came up with that only drawbacks, you don't use it anymore. Close it. And get to the molecular orbitals very as quickly as possible. That is what the very explain most of the stuff. But going through all the things in so much detail, rules, exceptions, and so on, there is one daily. Why it doesn't work is for me next. So I think that is what drives the students away from chemistry because they don't see there's any logic in it.
Right. I mean, I think that's a bigger point about all subjects, that the subjects develop scientifically in a certain chronological order. Should be taught in the same order.
No, they should not.
I think like we can talk about history with insights, then focus meeting that matters. And more clearly, a lot of less time was spent teaching that. People instead spend time more teaching ESR, how to do it. But the one that choose most today is
Yeah, exactly.
So you should get to that quickly.
Yeah. That I would say, as Fish points out, you start with, let's say, whatever is after true, say it doesn't work. Move quickly into that, speak from that. At the end, probably you should go back and explain why after truth fails. That will be a great learning.
the introduction slide to around this thing, and then maybe you get to the main thing.
In this high stable, right?
Yeah.
So if you give the problem to the students, right?
Yeah.
And they will write down the say concentration to be found, right? And they will put the concentration at moles.
Yeah.
And what they will end up in there will be a dimension of concentration or something like that, right?
Yeah.
But if this is not equal, right?
Yeah.
So how do you explain to the student that equilibrium constant is actually a dimension?
I mean, when they put this into the formula, right?
You choose the example, it's not that it is equal, right? Both sides, but if I choose an example
Yeah.
where a reactant and product are different in a stoichiometric ratio, still the
But eventually it will be the same, right? Like no matter what kind of equation you take, so even for this example, for this equation, right? Ultimately,
if you go back to A, right, in this one, right?
yeah.
Let's say C, D and A, B are completely different, they don't cancel out, right? I can choose one chemical equation where A, B, C, D are so different that the power to the concentration doesn't cancel out.
Yeah, but
So they will end up that the dimension will be.
but K is
They will,
but K is a constant, right? So I think no matter
yeah, so how do we explain to the student that K is actually dimension?
I mean it's let's see this. Like if they plug it, if they get a unit, thing, right? Then they're doing something wrong, right? If they
They
get
are doing wrong, but how do we explain that it is wrong? I can choose an example where A, B, C, D are different, right?
yeah.
And they will end up with the dimension of some sort of concentration. How do you tell that it is wrong and why it is wrong?
See, because this particular, like if, when you're using this document, it has to be a balanced equation, right?
Yeah.
It's a balanced equation. Your K is going to be like different dimensions. It's not going to have any not going to have any units. It's only going to have a number finally.
Yeah, but I can choose a equation, chemical reaction, they don't cancel out, right?
I think that's right there. So that the calcium carbonate will come to.
Yeah.
Because you don't take it on the solid. And of course, calcium oxide and calcium carbonate don't come. The only thing that is there is carbon dioxide. So the Kc over there is like units of carbon dioxide concentration. So right there you have example of the equation
Yeah.
where you have a
Concentration.
net concentration
Yeah.
of sterility.
Yeah. So if you take that example, yeah.
Okay. I mean, like, I don't know, maybe I'm not answering this correctly, but it's the value, the K is basically supposed to be a constant. So you have to say that, you know, it's something that you're using to determine the extent of the reaction.
Yeah.
You should not be having units, and even if you have units, those units should not have
Yeah.
any real implication.
Yeah.
That's the only thing I could say, like, for example, this.
If you put the pressure,
Yeah.
then you will end up with pressure, right?
Yeah.
But it will be wrong.
Yeah, correct. So the thing is, so like how I'm going to deal with this if the student
Yeah.
is doing it, right? He does most of the process correctly and definitely got this number. The number is correct, the numerical value is correct. But if he still has some units, I'm going to ask him, okay, listen, look at this constant as a definition of what your reaction is doing, what is happening. Forget about the fact that I may have to talk some points for the fact that they put a unit, but in this context, the unit has no meaning for the constant, right? It has no value. So I mean, like, it should not be coming at all. If it's a constant, equilibrium constant, I can only get a number that defines like the magnitude of the reaction happening.
Yeah, but if the students, they will plug this number and concentration, give it dimension and they will listen. So you have to, I mean, there is a reason why they are dimension.
Yeah. Okay, I'm going to ask you later. I'm going to say that I'm not sure about this. What is your approach?
So they comes from the activity, right?
Yeah.
So they are kind of a pressure divided by your P0, the unit pressure. So they are kind of P by P0. So there is the activity.
Okay.
In thermodynamics activity. So when P by P0, this pressure unit will cancel out, right?
Yeah.
For individual component.
Correct.
So they will cancel out. Yeah. So the pressure that you are writing here, it is actually P by P0, standard pressure.
Okay. Yeah. This one, right?
Yeah. And that origin is
The partial pressure, yeah.
Partial pressure, right? That origin comes from your thermodynamics activity.
So what I didn't understand correctly,
Yeah.
what you are saying is PC, PD, PAP themselves are dimensionless. And therefore they raise to any exponent will still remain dimensionless.
Yes.
Yeah, what should go there is dimension.
Yes.
Then we assume the activity to be one
Yeah.
situation and therefore we go with
Since
the
it is
denominator.
dimensionless quantities raised to various exponents, it doesn't become any dimension at the end.
Yeah.
You don't know that yet.
Yeah, and I think that's the way in almost all of the scientific studies. That really the activity
The activity
is
matters, yeah.
used and not the concentration.
Yeah.
So then we say what the heck, this is concentration.
So that's how many students they will put up the units and you have to give them 0.
Yeah, no, I would do that. If the thing is, if they've done something to the maximum possible extent, right? What that we understood what we even we like now, right now, I'm learning something new. I'm not exactly that. I probably knew it, but I forgot it. So,
That's kind of interesting because in biology we often measure the dissociation constant in micromolar. So we made the KD is mentioned as a micromolar. Already used an idea.
Yeah, that's because you have recognized the fact I'm not using activity, I'm using concentration, so I carry my units. If you want to be very strict about it.
It should
You know,
not be.
we'll take it as A is dimension. See, yeah, I think the best way to look at the activity is if I want every concentrated solution for something, not every molecule is in a position to react.
Yes.
So the capability to act, able to react in a concentrated solution is not the entire material, only some of them are being bedded inside, you know, they can't even react. So the activity is less than one. So if I take dilute solution, every molecule has the same probability of reacting, and therefore there the activity is equal to one. Everybody is willing to react. So chemists worry a lot about, you know, is all the molecules are taking, are they in a position to act? No, particularly if they're concentrated. That's where the activity is. That's where I look at activity.